like a compliment, then yeah, then I, won't be on the top of her list anymore.
Okay, let me say a couple of words about the next homework. Let R be a community ring of identity. You say that R is zero dimensional if every prime ideal is maximal. By the way, how many of you have already heard those kind of words before, prime and maximal? We're going to formally define this in a moment, but number A, show that any zero dimensional integral domain is a field. Number B, show that if R is finite, then R is zero dimensional. So any finite ring has this property that every prime ideal is maximal. And finally, give an example of an infinite zero dimensional ring that is not. So how many of you have ever seen the old thing in your first algebra course that any community ring of identity has maximal? I heard that theorem before. If you have a community ring of identity, you always have a maximal ideal. Well, we're going to get to that theorem very soon. The next problem is it shows you that when we do the proof, that there's actually something going on here. So consider the community ring of identity just the direct product of countably many copies of Z2 under pointwise addition and multiplication. For each n in the natural numbers, show that set of elements that I built, Mn, which is a set of all sequences in here, where the nth coordinate is 0 is in fact the maximal ideal of R. Show that I, which is the direct sum of Z2, is actually a proper ideal of ring R. And show that I is not contained in any of these maximal ideals here. And as a challenge, I say they're good luck describing the maximal ideal that contains I, which we will prove that such a thing exists. If you can write down generators of relations or anything like that for the maximal ideal that contains that particular I, I'll give you an A in class. Take off the rest of the semester. The last one's kind of for fun. Let R be a ring. We will not assume at the beginning that it's either commutative or has an identity. Show that if R is a finite ring of P elements, where P is a non-zero prime, then R must be commutative. Show that if R is a finite ring of P elements where P bigger than 0 prime, then either R is a field or R has trivial multiplication. And by trivial multiplication, what I mean is the multiplication where the product contains 0. C, find a non-commutative ring with 4 elements. And in D, give an example of a ring with a left-right ideal that is not a right-left ideal. What I mean by that in that notation is, give me something, a ring that has a left ideal that's not a right, or give me a ring that has a right ideal that's not a left. I don't care which one you do. You don't have to do them both. Okay, any questions on it? All right. Well, so let's get back to where we were. I want to move right on to something that you might think looks familiar, because it does. Let R be a ring. And I and R are ideal. In the quotient group, by the way, remember a ring is first and foremost a group. And in fact, it's first and foremost an abelian group under addition. So any ideal I is a normal subgroup. So I know what this is. I'm all warm and fuzzy for this because this is just the quotient group. So I also claim that I can turn this into a ring, and all I've got to do is tell you how to multiply things. So let's say remember our math adage, if it ain't easy, don't do it. It should also be a coset. What's it gotta be? Yeah, R is commutative. So it's R mod I. or R as identity. So does R mod I. And the identity here would be coset 1 plus I. As you can see by this rule that that's the way the multiplication will work. So I am only in this proof going to show that multiplication is well defined. Everything else follows from ring property star, right? And it's actually pretty straightforward to show that this is a ring. For example, if you wanted to show the associativity, it just follows from the associativity of R, etc. The really the only meat to this is why is it the case that the multiplication is well defined. So, to this end, right, we got to show the multiplication makes sense because if you say tomato and I say tomato, and you say potato and I say potato, then potato, tomato has to be potato, tomato, whatever it is, right? You guys get the gist, right? So, how do we go about this? Well, what I want to do is this. Because of the fact that the coset A is the same thing as coset X, and the coset B is the same thing as coset Y, I've got this going on, right? So if I look at AB, let's just straight up multiply this. This is X plus I1 and Y plus I2, and you just FOIL that up. Be careful with your FOIL though, because the ring is not necessarily commutative. This is XY plus XI2 plus I1 Y plus I1 I. Now notice it is important here that I be an ideal. And when I say ideal, I mean two-sided ideal. Because notice this animal is in I, and this animal is in I because it's a right ideal. And this is in I because it is a, yeah, that's right. And this is an ideal because it's a left ideal. So this whole bunch here I can call alpha in I. So I'll prove the cosets are the same and the multiplication is well defined. Okay. Any questions? Yeah. So you might, man, this is coming. This was talking about quotient structure. I have to start talking about kernels and so forth. And what's coming just around the corner is the analog of our isomorphism theorems, this time for rings instead of just for groups. The homomorphism of rings, the kernel of that is an ideal of R. Shown that last time. And if you have an ideal, on the other hand, if you start with an ideal of R, then is ring apomorphism. Let me point out, of course, that this homomorphism is clearly on, right? Because an arbitrary element of R mod I is this form, R goes to it, so it's on to. It's easy to check if this is a homomorphism. It is, we already know, a group homomorphism. So all you need is the fact that multiplication works. So that is just really sort of a reminder that the kernel of a homomorphism is an ideal. And when I have any homomorphism from R to S, then, right. So if I have a homomorphism kernel is ideal, and if I have an ideal, then this homomorphism is actually an epimorphism of rings. So in other words, if you have an onto ring homomorphism, basically that corresponds to, modding out an ideal. So, as promised, let's hit up the isomorphism theorems. And I will probably be kind of sketchy on the proofs here, because the proofs for the isomorphism theorem of rings are the same thing, essentially, as what we had in groups. In fact, whenever I produce any of these homomorphism theorems, really what it is it's just the homomorphism theorem from the group situation. In fact, the abelian group situation with a little multiplication sprinkled in because groups weren't exciting enough. So to 14. I am going to make this more general statement here, and I'm going to rip off this corollary, the well-known first isomorphism. Yeah. Is a homomorphism of rings. And I and R is an ideal. Two-sided, of course, contained in the kernel of F. Then there's a unique ring homomorphism. There's a unique ring homomorphism. We'll call it F bar from R mod I into S, such that F bar of R plus I is equal to F bar. Let me make some remarks about this. the image of that bar equals the image of that. That should be fairly obvious. And the kernel of F bar is the kernel of F mod I. And so let me make a remark. Given the veracity of the statement of this theorem, then F bar is an isomorphism. Let's see what we need. F bar is an isomorphism if and only if, well, we know the image of F bar is the image of F, so that's on. And you need for the kernel of F bar to be 0, so you need I to be the kernel of F. So let me just sketch a couple of details of this. So we've done the same thing actually for group theory. So really what we need, so we need that F bar is well defined, and this is done. Because the well-defined function is done at group theory, right? Of course, uniqueness is determined just by this, and I'll leave this as an exercise. The kernel of F bar is equal to the kernel of F mod I. But remember, the kernel of F bar is everything in R mod I that goes to 0. Everything that goes to 0 here is what's in the kernel of F. And you get that right here. So this is basically the analog of the same thing we have in group theory. Now I'm going to use this to get the isomorphism theorems that look essentially the same. Suppose that you have a ring homomorphism from R to S. Then F induces an isomorphism. F bar from R on kernel F onto okay. So really, all you have to do to get this induced isomorphism is take the previous result and replace S with its subring the image of that. And if you do that, then the rest of it follows. That's the first isomorphism theorem. Okay. The second one is I also report as corollary. If F from R to S is a homomorphism, I and R, J and S are ideals. Again, two-sided, because we're going to be talking about functions here. Such that I want F5 to be contained in J. So the image of the little piece here, I, is always inside of J in the target. Then F induces a homomorphism. And again, I'll call it bar. And it's induced this way. Of course, you have F bar of A plus I. You want this to barf out a coset over here. And F A plus J. This is the same as the group theory stuff again. What is this condition for F, I's, and J? This basically keeps this thing well defined, right? Because what this guarantees F, I's, and J is it takes the trivial coset, everything in I inside J. If F of I was not in J, then you might take something in I over here to a non-zero coset over here, which is ridiculous. There's no way that's going to be it. There's no way that's going to be a group on the board. So, let me collect some more facts about this. Additionally, F if and only if image of F plus J is all of S, and F inverse J painted I. This condition is what you need for onto, because you're generating everything in S with the image of F plus J, right? So that gets you all of that. And this condition here gives you oneness. Okay. So again, I know I'm going kind of fast and furious on the ring homomorphisms, but they really are similar to what you have in group. See if you can work through that. And if not, I would be happy and pleased to go over it with you. So, here's another, here's the analogs of isomorphism theorems 2 and 3. Okay. There is isomorphism of rings. I intersect, or I mod intersect. That's more. I plus J mod J. This should probably look familiar, right? Because that's the second isomorphism here. And actually the proof is the same, right? We basically constructed a homomorphism. We had all that business back in the group theory days, the normality. We don't need to worry about that here because it's in a Billian group. All you have to do is verify the multiplication works. In a similar fashion, you get the third isomorphism theorem, the correspondence theorem. If I so this time I add a little extra caveat that I is contained in J. Then J mod I and R mod I is an ideal. And of course, if I ever have an ideal, I can mod out by it. And so what happens? I do this. I take R mod I mod ideal J mod I. That's more to R mod J. Now, what follows from this, just like in groups, is following theorem, whichever form, because it's the correspondence follows from this. So statute theorem here. So let I and R. Then there is a one-to-one correspondence. There's a one-to-one correspondence between ideals of R containing I between this ideals of R containing I and ideals of Y. And the correspondence is given this way. Suppose that this is a J here. So J is an ideal containing I, and this corresponds to my I. So here's the takeaway. And again, this is just like the group theory thing. Here's the takeaway. Every ideal of R mod I is of this form, right? If I had any ideal of R mod I, it is the form J mod I, where J is an ideal of R that contains I. Okay. So that is kind of a whirlwind tour of the isomorphism theorems, correspondence theorem. They're all just like the group theory stuff. The proofs are essentially the same, just sketches of a couple of things that I did. They're essentially the same, but you might try to work through the details, especially check the multiplication. If you have trouble, let me know. Okay, any questions? Okay, so now I'm going to talk about certain types of ideals. And this, to me, this is one thing that makes ring theory kind of interesting, is, or at least, especially in commutative algebra, which we'll be branching into pretty soon. often one studies rings by their ideals, right? There were various types of groups, right? There are normal subgroups, right? And those are the ones that we consider. So for rings, the analog of subgroup for a ring is subring. The analog of normal subgroup for a ring is an ideal. And we knew things that were better than normal. For example, characteristic, different flavors of this, flavors of normal subgroups. But to me, in ring theory, it's a little bit richer. So I'm going to introduce types of ideals. And you can talk about some of these you can talk about analogously with group theory, in particular maximal ideals, but they're so much more fun with ring theory. Definition. Okay, the first thing I want to, how many of you have ever heard of the maximal ideal? This is very fundamental in ring theory, a maximal ideal. We say M in R, and I mean strict. When I have a maximal ideal, and a prime ideal later, I'm going to mean that strictly contained. A maximal ideal, because otherwise it would be stupid, right? Because you'd say, oh, look, any R is the maximal ideal. We say M and R is maximal ideal. Yeah. There is no if there is no ideal property contained. That is to say, with an ideal in, so it just means maximal, just because you can't shove any other ideal between it properly in between that and the ring. And before I stampede off, let me give you a couple other definitions, and then we'll get some examples. So, companion. We say the ideal, again, strictly contained in R, is prime. Okay, somebody tell me what a prime integer is. Right, its divisors are only itself in one. Does anybody know another definition for prime? How many of you have heard that one? A prime number, if it divides the product of two things, it's got to divide one. That's what it is for ideals in the following sense. So here for ideals, this is actually kind of a good mnemonic device to keep in the back of your mind. Containment is to ideals sort of what division is to elements, right? So dividing an element, it's very similar to the notion of containing an ideal, right? What it means to be prime is if P contains the product of two ideals. And this ideal, remember, is the sum of AI, BI. Right, it's the product of ideals, then it has to contain one. We're going to find out that there is a connection between these ideals or these types of ideals. Let me give you a notation and then I'll collection of prime ideals. It's called spectrum. So, and it's often written this way. P, system P and R. Sometimes people call the collection of maximal ideals the max spec of R. Collection M, system M and R. So let's look at some examples here. Let's start with the integers because they're, my goodness, it seems like they're the prototype about everything. Can anybody give me an example of a maximal ideal? Let me start off with these. Look at the collection of all even integers. This is, we've seen as an ideal, right? Because it's all multiple of 2. Okay, suppose you have a slightly bigger ideal. I don't know much, but I know this much. Anything slightly bigger than that has to have an odd in it. Everybody cool with that? If it's bigger than that, it's got to have an odd number. Let's say 2n plus 1, right? But if it's an ideal that's bigger than that and it contains 2n plus 1, and it contains that contains 2n, so it contains 1 plus 2n minus 2n, so it contains 1. So anything that properly contains that ideal is all the n. Everybody agree with that? And in fact, you can use a similar argument to show that PZ or P is a maximal. And in fact, you can show that's an if and only. Because if you have an NZ where n can factor down properly into AB, then that's contained in the ideal generated by A. So it's not maximal. Everybody okay with that? Yes.
When you say max spec of R's and such a M is maximal, is that saying it's a set of maximal prime ideals?
No, it's just a set of maximal ideals, but it turns out that we're going to see later that maximal ideals are always prime. And in fact, these ideals are always prime, right? Because if you have NZ, N is contained in PZ, and that means NMZ contained in PZ. So in particular, P divides NM, right? Because NM lives here, right? So NM must be a multiple of P, so P divides this. Therefore, without loss of generality, P divides N, so PZ contains NZ. Right? So all these ideals are in fact not only maximal, they're prime. And there is one more prime. Actually, Z has one more prime on it, but I'll let that off. Anybody know what it is? Can't be itself. right? Because the problem is that I demand that these all be prime. Why don't you go to the other extreme? Zero. is prime ideal. Because if zero contains NZ, MZ, and zero contains NM, the only way that can happen is for one of N or M to be zero. This is very, in one of my first years of teaching, like the undergraduate version of this, I had somebody who was like a high school teacher who was like taking the class kind of continuing ed. And I thought he was going to get in a fist fight with me when I told him zero is a prime number. It was very upsetting. But it is actually zero. That's why if you look in a number theory book, if you've ever wondered about that, if it's somebody is a careful author, number theory book, they will often say, let P be a non-zero prime. Because actually zero is a prime, but it's kind of degenerate. Misbehaves. And actually, you can also see that it falls directly from the definition of prime, because if zero divides A times B, then zero must divide either A or B. Right? Because the only way that zero can divide anything technically is for that thing to be zero. I'll talk about that later. Let me give you another example of something that's not just the integers. So you might try to check these examples yourself. I mean, two of them. Okay, what do I mean by this? This is the set of X, Y, where P is polynomial in two variables over the field F. We'll say that F. Now you can pretend this is the real, if you're comfortable with it. So it's like every real value or every polynomial that has real coefficients in two variables, right? Here are some maximal ideals. You'll be able to see why this is true later. This is the set of the ideal generated by X and Y, like we talked about. Let me clear this up for you. This is anything in this form. Another way to look at this is the set of F X Y such that F X 0, 0. This is in fact the maximal ideal. This is basically all linear combinations of X and Y. So is this. So is this. These are all maximal ideals. Here's another one. If numbers, then y x squared plus 1 is maximal. This is not true if f is a complex number, because the same factors down further. The ideal generated by x, which is just a set of x times p x, y, is prime, but not maximal. Because x is strictly contained in x, y. And in fact, you can generalize that example to take any irreducible polynomial in two variables. If you can't factor it any further, it will generate a prime ideal just by looking at multiples of that. Right? And again, in this range, 0 is still a prime ideal as well. let me give you one more example, which might kick you down the path on homework. A1, A2, so this is direct product of C2. Let M equal a set of principles like this. I meant to write Z2 here, but it's the same thing as F2. It's all the same. Let me point out, let me give you a quick proof that this is in fact is an ideal. What happens if you add two things that have 0 as the head? You get a new string where 0 is at the head. Everybody agree with that? So it's closed under addition. This is in fact a subgroup. And it's a vacuum cleaner, right? Because what happens if you take something that looks like this and multiply by any sequence that you want, the resulting product will still have a 0 in the beginning term. Everybody agree with that? So is everybody cozy with the fact that this is in fact an ideal? Why is it, Max? Well, let me give you a quick proof of this. Suppose M strictly contained an N. I want to prove that N is everything in there. Well, so there exists something like this. And notice zero, B2, B3, B4, and 0, 1, 1, 1, whatever, are both in M. Everybody agree with that? So they both got a 0 at the head. So what we have is 1, B2, B3. This is in N. This is in M, which is contained in N. And this is in M, which is contained in N. What happens when I add these three happy things up? I get a 1 in the first coordinate. B2 plus B2 is 0, because this is Z mod 2, plus 1 is 1. 1 is 1 forever. So the identity of R is in N, so N. So this is a maximal. Everybody okay? Okay. Let me give you theorem here. So prime ideals, maximal ideals I find kind of easy to understand. They're as big as possible without being a whole ring. There you go. Prime ideals, I find it a little bit harder to wrap my head around because, okay, P contains the product of two ideals means that P contains one of them. Here is an element-wise way to think about this theorem. Unnumbered. If P is an ideal with property everything implies A and B are P is A is B, then P is prime. Yeah. R is commutative. Complex. So let me finish off this mark here. So the takeaway for that. Another good plug for why I like to be fast. R is commutative. Then P and R prime ideal. Implicitly P is prime. If and only if A, B, and P implies A, B, P. Okay. We will talk further about this next time. Any questions on this? I like this in the community setting because you don't have to worry about the clunky ideals. There's an element wide way to look at it. That is, price for two things in prime, theme one. Questions? Okay, well, yes, go ahead.
This is a silly question. For your notation for ideals, do you use like is it a separate notation or the less than or equal to sign?
No, I don't use the group or anything. I use the curve.
Okay. Yeah. Thank you.
Let me plug the math club today. Robert Lund, some of you may know because he was a professor here for many, many years. Maybe not many, but many. He will be here in the math club, and he's going to be talking about. He's actually one of those dudes who's pretty well known among the the modeling kind of people. I think he's even been on the Weather Channel and crap like that. So he's really knowledgeable, and he's got kind of this interesting model about climate changes and effect on hurricanes. So I would encourage you to be at that. Other than that, don't forget there's homework today, and y'all have a good weekend.